All right, good afternoon, students. It's my pleasure to welcome you again to your Organic Chemistry 1 class, BLC. It is my pleasure to be teaching this subject. I enjoy teaching all chemistry classes, but I will tell you quite honestly that this is one of my favorite classes to teach. As I've explained to you in the Zoom meeting, I've worked extensively in organic chemistry for a good part of my life, and so this subject is very close to my heart, and it's a pleasure to teach this subject to all of you. So I'm sure we're going to have a good session together despite the circumstances. I will, however, warn you of one thing. Again, as I've said before, this is a jam-packed course. There's a lot of material, and so it really requires that you stay on top of things, that you do the readings, that you do the exercises, and I would strongly encourage you to do this religiously right from the beginning, because as you know, things will quickly pile up at the college, and so you want to hit the ground running and start strong right from the beginning. So please notice again here that you have my contact information. However, the easiest way to contact me is by far by MEO. I try to check my MEOs every day and to respond as soon as possible. So if you do need to communicate with me, that is the best way. One more warning, Unit 1 is going to fly. I am going to go very, very quickly in Unit 1, and the reason is simple. This is review. And so if you are finding some of the things there challenging, that means that you have to go back to NYA to NYB and to make sure that you brush up on these basic principles. Knowledge is cumulative, and so organic chemistry continues and is built upon the principles that you've learned in NYA and NYB, and that's why Unit 1 I will go very quickly. Fear not, I will slow down as we get into new material, but for the moment it's going to be moving fairly rapidly. So as already explained, you have the textbook paper copy here that's available. If you want to get it online, that's perfectly fine by me. The lab manual information will be uploaded when the time is right. You should have the molecular models with you. You are going to find that it's much easier to visualize and to understand many of the structures and the reactions if you have these models. So this is not a luxury, it's a necessity to have these models. The evaluations, as already explained, follow what's written there, and I already gave you a tentative schedule of class tests. So if you have any questions about any of these things, again, please don't hesitate to contact me. So Unit 1, as I said, is going to be mainly review, and this is why I'm going to be going very quickly. These are the chapters in the Klein textbook. The textbook, by the way, is excellent. We have reviewed many different textbooks for organic chemistry, and this one, in my mind, and in many other teachers' perspective, is by far the best. It's a little bit wordy, it's a little bit in detail, but it's done in a way that essentially it answers many of the questions that you could and should have as you study this subject. We will then move on to alkanes and cycloalkanes, so simply carbon and hydrogen molecules. Then we'll talk briefly about different types of organic reactions, and then stereochemistry. This is a subject that many people find challenging, but again, I will do my best to make this as clear as possible. It is a fascinating topic, and again, the molecular models will be very helpful in understanding what this is all about. Then we'll talk about the properties, chemical properties of alkanes that we've discussed before, and then of alkenes. And this is by far the largest of the chapters. Alkene chemistry is rich and allows a lot of versatility, and that's why this is going to be a key chapter in this course. The chapter of alkynes is sort of like brother and sister in terms of the type of chemistry here. So if you've understood well this chapter will be a breeze. The next unit is nucleophilic substitution and eliminations. This is a bit of a challenging chapter also, as it dives a little bit deeper into mechanisms, organic chemistry reaction mechanisms, the strengths and limitations of these different mechanisms, and finally, arene chemistry. So this is aromatic compounds. This is truly a category of its own. The type of chemistry that is done here is very different from a lot of things that we've seen before, but it's rich and important and applied in many different ways. So in a nutshell, this is what we are going to be doing this semester. A lot of fun. I won't go through this, but this is the various topics that we are going to see. Most of these represent review. Remember that on the left-hand side of the slides, you have the place in Klein, where the information in the unit is found. And on the right-hand side, typically, I have suggested problems that you could do in the textbook. You can do more, but I strongly recommend that you at least do problems that are given to you. If ever you can't find the answer to the problems in Klein and you would like to receive them, send me a mail. I will search out for the answer and bring it to you. If you don't understand the textbook question, then I will take time to explain it to you. But I will always follow that strategy, give you first the answer, and if you can't understand it, then I will give you additional information. So let's begin. But before we begin, I want to start with a quote that is not from Klein, that is from our previous textbook, which is McMurray. And I love the quote in McMurray. And the quote, actually, before I go there, let me just go back a second. I forgot to mention something. In McMurray, notice this molecule right here. So this is rofecoxib, also known as Vioxx. And this is on page 1 of McMurray. This molecule here, which used to be sold as a drug for pain medication, this molecule here, page 1 in McMurray, was actually made the first time by one of my colleagues in the lab at Merck, where I worked for 12 years. So this is proof enough, isn't it, that the organic chemistry world is close to my heart. I open the textbook and the first molecule that I see was made by one of my colleagues. Cool. So with that, let's go back to McMurray and read this quote. Please read with this with me carefully. When first approached, organic chemistry might seem overwhelming. It's not so much that any one part is difficult to understand, it's that there are so many parts, tens of millions of compounds, dozens of functional groups, and an apparently endless number of reactions. This is the complaint that many students will bring. Well, McMurray acknowledges this challenge, but brings a wonderful, very true answer to this challenge. With study, though, it becomes evident that there are only a few fundamental ideas that underline all organic reactions. Far from being a collection of isolated facts, organic chemistry is a beautifully logical subject that is unified by a few broad themes. When these themes are understood, learning organic chemistry becomes much easier and memorization is minimized. Notice the language here. Beautifully logical subject. You see? I'm sure there are going to be moments where you don't agree with Mr. McMurray, but I would strongly urge you that when those difficult moments come, that you come back to this quote and reread it and find ways to figure out how this is indeed the case. And I will be highlighting those few fundamental ideas so that you are able to put together the pieces that you are going to be taught in a way that it makes logical sense and that hopefully it's beautiful and unified and clearly understood. And here's a little bit of a molecule with a lot of history. This is vitamin B12, and a molecule that was first synthesized many decades ago by a great organic chemist. I believe it was from Harvard. And as you can see, the molecular complexity that is there. Look at this cyclic structure, polycyclic structure. A cobalt atom in the center that is complex to, again, all of these appendages that are fairly complex. Phosphorus connection here, all of these different groups. So, yes, a lot of fun and a lot of interesting things to study. So, let's begin, and we're going to start again with things that you've already seen in the context of NYA and NYB. Lewis structures. Lewis structures are 2D representations of the bonding arrangement of molecules. Each dash that you see represents a covalent bond, and one bond represents 2 electrons. Sometimes you'll also see pairs of dots around an atom. And this is what we call a lone pair or a non-bonding pair. So inside a bond, you have bonding electrons. That's the line. When you have dots, those are lone pairs or non-bonding electrons. Generally speaking, atoms follow the octet rule, what we've discussed especially in NYA. The octet rule states that atoms will attempt to find a bonding arrangement that completes their valence octet. Remember that valence is the outermost shell, the last shell. And so obeying the octet rule means that you're able to complete that last shell either through donation and accepting electrons in ionic compounds or by sharing in covalent compounds. For example, draw a Lewis structure for the following molecules. So NH3, N is the central atom, and we have 3 hydrogens around it. Is there anything else that we have to add? Yes, because nitrogen has how many electrons? Well, if you're not sure, go back to your periodic table. That should always be right next to you, and you'll see that it has 5 valence electrons. 3 of these valence electrons are bonded with the hydrogens, which means that you have one more pair, or 2 electrons, that are non-bonded that need to be identified on the central atom. This is what the Lewis structure of ammonia looks like. If you forget the lone pairs, you've made a mistake. Draw the Lewis structure for the following compound. This is formaldehyde. You can pause the video and write the structure, and then when you're done, unpause. And so carbon is going to be our central atom because this is the one that participates in the greatest number of bonds. And then you have to find a way to decorate the carbon atom with hydrogen and oxygen in a way that will make sense. And this is the way that it will make sense. It's the only way. And so notice that we also have 2 lone pairs on the oxygen atom to make up the 6. So 2 of these oxygen electrons are bonded, and 4 of these, in the form of 2 lone pairs, are non-bonded. So these are the correct Lewis structures. It is imperative that you are comfortable with doing this. If you are not, then make sure to take time to go back to NYA and to do the problems in Klein that allow you to practice this. This represents the ABCs of everything that we're going to be doing later on in this course. Few hints. Hydrogens only form 1 bond, so they're always at the edge of the molecule. Halogens usually are also terminal atoms, so at the edge of the molecule, to have their full octet. Carbon is always a central atom and follows the octet rule in stable compounds, but not always in unstable intermediates. For example, carbocations. Carbocation would be a carbon that is positive, and it would be lacking 1 electron. Those species can exist. They will be short-lived, they are unstable, but they do exist. We'll talk more about that. Nitrogen, oxygen, and fluorine always follow the octet rule. So as it says here, all of you are responsible for reviewing the material in NYA and NYB. I'm making a brief review in this unit. I'm going very fast, but it's your responsibility to bring back to mind all of these important principles. Valence structures should be consistent with the following known valence of the elements. Valence is the number of bonds that an atom usually forms. For example, carbon, you know it has 4 electrons. So 1, 2, 3, 4, using the 4 quadrants, north, east, south, west. And that's how we position the electrons. Nitrogen has 5, oxygen has 6, halogens have 7, hydrogen has 1. And this Lewis diagram explains very simply how many bonds can be made and if and how many lone pairs exist. This explains the valence. This can be tetravalent, maximum 4 bond, 3 bonds under normal circumstances. Nitrogen can actually make 4 under certain circumstances. The valence, and here you've got some examples of molecules. This is methane, this is ammonia, this is water, this is like a hydrofluoric acid or hydroiodic acid. And you've got other examples of other types of structures that are also possible with different hybridization states. We'll talk about hybridization if you've forgotten what that is all about. So this is a nice little diagram or table that summarizes a lot of very basic information that's important for you to know. Draw Lewis structures for the following compounds. So again, here, pause the video, write the structures, and then I'll give you the answers. So for our first compound, we see that the number of hydrogens per carbon lead to a saturated structure. So carbon and carbon, 3 and 3 attached together. This is methanol, methyl alcohol. So we've got carbon and oxygen bound. Don't forget the lone pairs and the rest of the hydrogens around. There are exceptions to the octet rule. Hydrogen, we said, only makes 1 covalent bond. Some molecules with beryllium, boron, don't have 8 electrons in their valence shell. We'll look at some examples here. Some atoms that are in lower periods have expanded octet, so are hypervalent. But most of the time in organic chemistry, we won't be dealing with these structures. This is more in the context of inorganic chemistry. So please write the Lewis structures for the following molecules or ions. Please pause the video. Alright, so for our first compound, beryllium chloride, this is what you get. Don't forget the lone pairs. CH3, that's a carbocation, not stable. This is not a happy molecule, but it does exist. So you can see that carbon has not 1, 2, 3, 4, but only 3. So we're missing an electron here. So this does not obey the octet rule. This is not stable. Formal charges. The formal charge of an atom is calculated by comparing the number of electron an atom possesses before bonding to the amount of electron it possesses after bonding. And so you can calculate this very simply in 2 different ways. First one, you take the number of valence electrons in the free neutral atom. Carbon, for example, has 4. Let's say that in a molecule, like the one we just saw, like this, instead of having 1, 2, 3, 4, it has 3. So you say 4 minus 3 gives us 1, or plus 1. So the charge is plus 1, as we saw right here. Okay? So you can calculate it this way, or you can also calculate it valence electrons in a neutral atom minus half the electrons in the bonds plus the electrons in the lone pairs. This is a bit more complicated, but it will give you the same answer. This is involving bonds and lone pairs in your calculations. Formal charge is used to indicate when an atom in a molecule is electron deficient or has an excess of electrons, which explains why there would be a charge. Here's a summary. Let me just walk you through carbon. So we know that carbon has 4 valence electrons. It does here. However, it only has 3 bonds. So it has 1 non-bonded electron. This is a strange structure, isn't it? You might not have seen such a structure before. This is what we call a free radical. This is not stable. Why is it not stable? Does it obey the octet rule? 1, 2, 3, 4 of its own, plus 1, 2, 3 that it's shared. That's 7. Not happy. So this is not stable. Okay? This is a radical, and it will react. In fact, you might have heard about how it's important to eat antioxidants. Well, antioxidants will react with free radicals in the body and quench them, destroy them. And so radicals are highly reactive and dangerous species. In this case here we have 1, 2, 3 electrons. But it has a charge of +1 here because we are missing 1 in the atom. In this case, instead of having 1, 2, 3, 4, we have 5. So that means that we have an extra electron, which gives us the charge that we are observing, -1. And you can do the same type of calculations for nitrogen, oxygen, and the rest. So I strongly recommend you to take a look at least at nitrogen and oxygen carefully and to make sure that this makes perfect sense to you, as I just did with carbon. Charges typically don't require calculations. You just simply look at the structure and you know, based on what you know from the periodic table and the element, if there's a charge or not. Shorthand tricks. In organic chemistry, dots represent lone pairs and often are omitted. Instead, formal charge is used to denote the number of electrons surrounding an atom. This is cheating, okay? Cheating not necessarily in a bad way, but just to save time, okay? So if I was on the blackboard writing stuff all the time, you'd see me do this all the time. So instead of writing, like this is an anion, negative charge, and you can see that the oxygen, instead of having 1, 2, 3, 4, 5, 6 electrons, has 7, okay, plus the 1 shared. So it has an extra electron, hence the negative charge. Instead of writing this each time, often organic chemists will write this. And when you see the negative here, it means it has 1 extra electron around here. In other words, this. What I'm going to ask you to do is not to use this method, but to only use this method, even though some people use this. And the reason is to get you used to always seeing the valence electrons, the bonded one and the non-bonded ones in the form of a lone pair. Got it? Formal charge can help us determine the Lewis structure of a molecule or ion by applying the following rule. Number 1. The sum of the formal charges on all atoms in a molecule or ion must add up to the charge of the molecule or ion. In other words, here we've got a -1. Well, the formal charge of everything is -1. Simple as that. The Lewis structure in which the magnitude of formal charges are minimized is preferable. In other words, in some cases you might be able to draw different Lewis structures, but in some of the Lewis structures you have a greater charge. Generally speaking, use the one with the lesser charge. Minimize charges. That's usually the right one. There are exceptions, but that's rare. It is preferable that for most electronegative atoms in a molecule to be given the lowest, most negative formal charge. Again, this makes sense, and there are exceptions, and there's reasons for those exceptions. But if you have two options, to put the negative charge on a carbon or on oxygen, who you want to put it on? The oxygen. Why? Because oxygen is more electronegative. It is more able to stabilize that negative charge. Remember your periodic table information. You have a table with it that is entitled electronegativity. So you've got all the different atoms with their electronegative value. Remember, the fluorine is the highest electronegative element. It's got a value of 4. And so you would want to put negative charges on the most electronegative atoms. Use valence and formal charges to draw Lewis structures for the following species. Clearly mark atoms with a formal charge and show lone pairs on atoms that bear a non-zero formal charge. Here are two structures. Draw the Lewis structure, show all of the electrons and the formal charge. You can pause it and unpause after. So for our first structure, we have here what's called the amide anion, and that would lead to the following structure. So nitrogen, 1, 2, 3, 4, 5 is what it usually has, but it has an extra one, 6, which explains the negative charge. This is the formate ion, and you have 2 lone pairs and 3 lone pairs on this one, and a negative charge on this oxygen. 1, 2, 3, 4, 5, 6 is what it should have. It's got 7, hence the negative charge. Knowing where an excess or deficiency of electrons in the molecule is very important because all chemistry can be related to electrostatic interaction. I'm going to take a second here and explain this because this is so fundamental. Remember that quote from McMurray and how he explains that, organic chemistry can seem complex, but in fact it's pretty simple if you understand the basics? Well, here are the basics of the basics. A lot, not to say almost every chemical reaction is the result of electrostatic attractions, forces. So what are those? Well, you connect the positive with the negative, right? So if you can figure out where the positive and the negative are, you can pretty much guess how the reaction is going to take place. And so here you've got this anion that is rich in electronic density, and here you have this cation that is poor in electronic density. So what's going to happen? Well, the rich electronegative atom is going to react with the poor electronegative atom. This lone pair here, which represents the negative charge, is going to come and attack. Yes, it's very violent. It's going to come and attack the hydrogen and pick it up. And those two electrons here that make up this bond are going to jump on this oxygen here to give you the second lone pair, hence a neutral atom, and this structure here, which also now is neutral. Take the time to count the electrons on each of these structures and understand why there's a positive, why there's a negative, why it's neutral, and now what's happening here. We're going to do a lot of examples like this later on. Draw the Lewis structure for each of the following molecule or ions and determine the formal charge of each atom in the molecule. Show all lone pairs. So again, pause and write the structures and then unpause. So for the first one, we see that we've got a negative charge on the carbon. This is the only structure that works. This one is a bit more challenging, eh? Cyanide is an unusual structure, and so this is the structure that it leads to. So notice that nitrogen has 1, 2, 3, 4, 5, and carbon has 1, 2, 3, 4, 5, and it shares 6, 7, 8, so it obeys the octet rule, but it has an extra electron, hence the negative charge. This one's a bit more challenging. If you remember from NYA, cyanide and carbon monoxide were among the more challenging Lewis structures to draw. Add any missing electrons or double bonds based on the information given for these ions. So pause and do these two problems. So the answer is as follows. We're missing lone pairs on the bromine. Where's the positive charge? Well, it's actually on the bromine. How do I know? Let's count. 1, 2, 3, 4, 5, 6. 6 electrons in its immediate valence shell, which means that it's missing one, hence the positive charge. Is it stable though? Yeah. Why? Because of how it's sharing. 1, 2, 3, 4, 5, 6, 7, 8. So it still obeys the octet rule. For this compound here, this is the carbonate ion, and all of the lone pairs are as such. So a negative charge here of 1, negative charge here of 1, for the total negative 2. Vesper. Valence shell electron pair repulsion. Good memories from NYA, right? This is a theory that dictates the shape of molecules. So if you remember when in NYA you had a lab and you had all these molecular model kits and you had to build the different molecules, it was all based on Vesper. This theory states that electron groups around a central atom will repel each other to minimize repulsion, and that essentially dictates the shape of these molecules. Electron groups are single bonds, multiple bonds, and non-bonding pairs of electrons. That's what constitutes an electron group. Again, if this is far behind for you, go back to NYA and refresh your memory on these things. I will go through it a bit here. For the following molecules, draw a Lewis structure and a 3D Vesper sketch. Use a line to represent a bond or an electron pair in the plane of the line, the plane of the page. Use a dashed wedge to represent a bond or electron pair going into the plane of the page. Use a bolded wedge to represent a bond or electron pair coming out of the plane of the page. So this is to show 3D structure. So I'm not going to draw these. I'm going to let you draw them. This one's flat. This one is 3D. So this is sp3 hybridized. We're going to look at a few examples in the upcoming slides. So what's the number of electron groups here? You got 3 for the hydrogens and 1 for the lone pair. So that's 4. And that gives you the tetrahedral structure. Here you've got only 3 groups, and that gives you trigonal planar. Let's look at hybridization briefly. Again, this is all review. CH4 has been found to have 4 equal bonds in a tetrahedral arrangement. However, carbon's bonding electrons have unequal energies in the ground state, in the atomic ground state. You see what it looks like here? That doesn't explain how this is 4 equal bonds. So what we do is we excite, we promote this electron here from the 2s into the 2p. And that gives us the following structure. So now we're able to make 4 bonds because we have 4 unpaired electrons. So now we can make 4 bonds. The problem is these are not chemically equivalent orbitals. So what we're going to do is to hybridize them. So we blend the 2s with the 3 2p's, and that gives us 4 sp3. So s from that one, p, 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 hence the 3. A little 3 tells you how many of the p's are used. So sp3 orbitals. So now those are all hybridized, they're all equivalent, and allow us to build that structure as we know methane, carbon, natural gas possesses. Okay? So that's the, what they call the, how's it called? Flower diagrams, yes. Good memories again, right? So this essentially shows the overlap of the orbitals with the unpaired electron from hydrogen, the unpaired electron from the carbon, and the sp3. So this is sp, this is 1s, 1s, sp3, sp3, 1s, and the same here. And that explains the structure of methane. So the sigma bond, you could write sigma here, sigma here, sigma here, and here. Head-to-head overlap of atomic orbitals. And this is the best representation that we can use to explain and to show why and how atoms bond to each other. It's to allow this sharing of electrons through the overlap of orbitals. This is CH4, so now let's look at C2H2, so this molecule here. And of course the difference now is the double bond. So once again, we start with the ground state electronic configuration of carbon and try to say, okay, how do we explain that this can be made? Well, we're going to have to promote, again, 1 electron, just like before. And what we do now is we only hybridize 2 of the 2p and the s, and we leave unhybridized 1p orbital, one that's called pz. So now we have 1, 2, 3 sp2 orbitals. That allows us to make 1, 2, 3 sigma bonds. This is trigonal planar. And on top and below the plane, this unhybridized p orbital engages into a lateral, not head-to-head, lateral overlap of unhybridized p orbitals, which generates that double bond. So on top of the sigma bond, you build the pi bond. This is what causes the specific structure of CH2, ethylene gas. Ethene gas, sorry. What about this guy? Now it's getting complicated, right? Not really. It's the same strategy. Now we have ethine. So we're going to do the same kind of analysis for this sp hybridized. Remember, we went from sp3 to sp2 to now sp. So we start with the same ground state of carbon, and let you complete this. So please pause and try to figure out the rest of the hybridization for ethine, HCCH. Pause. Alright, so if you did this right, the first step is, of course, to again promote an electron to excite the carbon, and then to essentially only hybridize one of the p orbitals to give you sp, and this creates this sigma bond with the hydrogen, this sigma bond with the other carbon. It leaves you two unhybridized p orbitals, one that is above and beneath, so that's one of the pi bonds, and the other one is in front and in the back. That's the second pi bond. So you essentially have a sigma in the middle and two pi bonds over it. This is the sp hybridized. This is all from NYA, and this is all important to remember for organic chemistry. In NYA, we kind of just looked at it and then moved on, but for us here in organic, it's going to continue to be very important. The common hybridization in organic chemistry are sp, sp2, and sp3 for carbon. The hybridization can be found by knowing what's called the repulsion number, okay? And so the number of electron groups, if you have 4, that gives you sp3. If you get 3, that gives you sp2. If you get 2, that gives you sp. So natural gas, ethene, and ethine. Missing in carbon here. Well, not really. And you've got the angles, right? So the angle between this, 109.5, this is flat like a pancake, so that's 120. And this would be from carbon to one side to carbon to the other side. That's a 180. Okay? So I'll give you a minute to do the two problems on the bottom here. Identify the hybridization of each central atom and draw a Vesper sketch. Actually, it's already drawn. Already drawn. So just indicate the bond angles and the hybridization. So please pause and then unpause when you're done. Alright, so sp3 for this one, sp for this one, because you have 1, 2, 3 groups. This is, of course, sp2, and this is, of course, sp. Now for this problem here, this is sp, sp3, sp2, this is 180, 109.5, this is going to be 120. So that's all the answers for you. Polarity of covalent bonds and molecules. So this, again, is the table that I mentioned that you have at the end or with the periodic table. So fluorine here, 4, is the highest value. Francium, 0.7. I think it's the lowest, if I'm not mistaken. So, and cesium. So bond polarity can be determined by finding the electronegativity difference using Pohling's electronegativity table, which is what's right here. Electronegativity is an atom's ability to attract a shared pair of electrons in a covalent bond, meaning that if you have two different atoms bound together, they are not sharing electrons equally. And that's very important because it means that it creates a polarization. One of the atoms is going to be more negative and one of the atoms is going to be more positive. And in organic chemistry, when you want to understand reactions, you have to connect the positive to the negative more often than not. So understanding polarity in molecules is therefore absolutely essential to understand why chemical reactions are taking place the way that they do. In general, halogens, oxygen, and nitrogens are more electronegative than carbon. Hydrogen and metal are less electronegative than carbon. Carbon, of course, is our atom par excellence of interest here. Organic of carbon. And why are we so interested in organic chemistry? Because virtually all of the structures in biological organism and living organisms are carbon-based. So we have a bias to prefer to be interested in the chemistry of carbon. And also, please notice that carbon sits at a fascinating place because it has the greatest number of unpaired electrons. And so that allows the maximum number of bonds to be formed, the maximum amount of complexity. So carbon is truly special, truly unique in terms of its position in the periodic table. No surprise that it's so important in living organisms. Determine the polarity of the following bonds. So just take a minute, and for each of these, write partially positive and partially negative for these three examples for those two molecules. Now, of course, chlorine is more electronegative, so that's the polarity. In this case, oxygen is more electronegative, and so is in this case here. By identifying the shape of the molecule or ion and polarity of each bond, the overall dipole moment of the molecule can be determined. So now it's not just about individual bonds. No. Now it's about the whole molecule, which is way more important. Remember, if we want to figure out how molecules react together, it's not just about individual atoms, it's about the whole molecule. So polar molecules or ions have a net dipole moment. Non-polar molecules might have polar bonds, but don't have a net dipole moment. Okay? So here's nitrogen, and this is a heat map. So red means high electronic density, blue means low electronic density. So guess what's happening here? All of the electronic density from the hydrogen is being sucked towards the nitrogen, and on top of it, we've got this lone pair on top of the nitrogen, which is already a center of high electronic density. So notice how red the top here is and how blue the bottom is. So this is not only this is not only tetrahedral in its structure, but look at how polarized it is. And what's interesting, you can kind of change it by changing the nature of the atoms. If we swap the hydrogens for fluorines, now fluorine is more electronegative than nitrogen. So now it is pulling electron density away from the nitrogen towards the fluorine. So less red on the top here, and now more red rather than blue where the fluorines are. Look at how different these molecules appear, electronically speaking. Okay? So heat maps are an excellent way to visualize how these molecules exist and behave electronically speaking. Carbon dioxide, look at this. Blue in the center, poor carbon. He's getting all the electron density sucked away from him towards the oxygens. So the oxygens are red, but in this part here it's blue. CH2Cl2, so this is carbon in the center, and then you've got two hydrogens that don't have electronic density, but the chlorines that have a lot more. Polarity is important when investigating the intermolecular forces between molecules and the solubility of one compound in another. This is important in many different ways, as you can see, not just in reactivity, but also those physical properties. Review section 212 of the textbook and complete the associated problems. That's a little bit of homework for you. And that ends our lesson for today. I am going to ask you to complete all of the problems on page 18, and I believe also the next page also 18. No, it's only 18, and then next class we will resume after we correct this. Please make sure to have this finished for then, and then we will continue to move on. So until then, have a great evening. Don't hesitate to contact me if you have any questions, and I look forward to seeing you again soon.